Welcome back to week 5 of our course, Boltzmann Law, Physics to Computing. This is the 5th and last lecture for the week. Now, in the last few lectures, we have been talking about this gated quantum computing, where the idea is to manipulate the wave function through a sequence of quantum gates. And we just discussed two of the celebrated quantum algorithms, which do just that. Now, what we want to do in this lecture is actually introduce a different way of looking at this, of what these gates do, in terms of what are called Feynman paths. And the idea is quite general, but instead of looking at specific algorithms, we'll try to illustrate the main point by looking at just the Hadamard Gate, the one we started in lecture 2 and which is used as part of all these algorithms. And this illustrates the basic point that we want to get across. Okay. So what's the Hadamard Gate? If you remember, the matrix looks like this. This is the transformation matrix. So given a wave function, as you apply it, you transform it, and then again. So we have applied it twice here. And the interesting thing is, if you start from all up and you apply it once, it spreads it out equally between the up and the down. And then when you apply it again goes back to all up. And this spreading and then coming back, that's usually not something you can do with classical systems. And that's kind of part of the magic of quantum and comes from this negative signs here. And we'll talk more about this. Now, the Feynman path viewpoint gives you a different way of looking at it. So you could think of it this way. Supposing you start with the 0 state initially, and we know that after applying this Hadamard Gate twice, you get back to 0. And the reason is if I multiply the two matrices, I get the identity matrix. So I just go back where I was. So you could think of it this way, that you went from 0 to 0, but through one of two paths. One path is 0, 0, 0, and the other path is 0, 1, 0. And what is the amplitude of the two paths? Well, going from 0 to 0, that's this plus 1. You see, I've labeled the columns 0 and 1. The rows are also labeled similarly, 0 and 1. So this element is the 0 to 0. That's what I've indicated here with a plus 1. And this 1 over root 2, that factor I'm just writing separately here to avoid cluttering it up. Now next one again 0 to 0, that's again a plus 1. You go through the other path 0 to 1, 0 to 1, that's plus 1, and then 1 to 0, that's also plus 1. So when you look at the amplitude of each of these paths, the top one is 1 over root 2 times 1 over root 2, that's a half. And you look at the bottom one, that's the same, 1 over root 2 and 1 over root 2. And you add them up and you get 1. Now, consider the other outcome, the one that doesn't happen. As you know, you started from up, you ended up up. But you could have ended up into the other state. Right. Now, if you now look at the paths, what you'd see is 0 to 0 and then 0 to 1. And the other thing is it's 0 to 1 and then on to 1. Now this lower path, you'll notice, actually has one of these elements which is negative 1. Because here you're going from 1 to 1. That's this element. So that's the negative sign. So now we have two paths. Both have amplitudes half. But one has a negative sign, so when I add them up, it goes to 0. So that's the Feynman pathway of thinking of what happened here. That you could go from 0 to 0 by two paths which add up, and you can go from 0 to 1 by two paths, but then they subtract. And what I just described to you though is just a pictorial representation of the matrix math. That is, Mathematically, we just multiply these two matrices and we could come up with the answer. And when you multiply matrices, as you know, you multiply rows into columns. So when you're trying to go to 0, it adds +1 times +1 and then +1 times +1. But then when you're going to 1, it's +1 times +1 and then -1 times +1. So that's what is represented with these paths here. But basically it's just representing what the matrix multiplication tells you what's happening. Okay. Now if you had many of these Hadamard gates all applied sequentially, so 0 at time steps 1, 2 all the way to capital T, then you see now you'll have lots and lots of paths, because going from 0 to 0 or 0 to 1, you have all kinds of intermediate paths that you could write down. At every time step, there are two possibilities. It can be 0 or 1. So overall, you have 2 to the power t total paths. And half of them, 2 to the power t minus 1, end up at 0. The other half end up at 1. Now, if you had n qubits, here it's just 1 qubit, but supposing you had n of them, then you see at every time step you'd have 2 to the power n configurations. And so now the total number of paths would be 2 to the power nt. So that's the number that determines how many paths you have, how many qubits, and then how many time steps, or what is the depth of the gates. Okay. Now, if you were doing this with a probabilistic circuit, you'd still have the same number of paths, right? Because it's the same thing. You have, maybe you can think of a classical thing, which is 0 or 1, and which evolves in time probabilistically. Well, in that case also, starting from some initial state to a final state, you'll have 2 to the power nt paths. But the difference is that you see when you draw the paths for a classical circuit, like we did at the end of week 3, the amplitudes are determined by this positive matrix, the classical transition matrix. Whereas now, in the quantum case, it's based on this complex U matrix that we have been talking about, where each amplitude is a complex number. Does that make a difference? Well, not really, if we are just going to multiply the matrices. If we are going to write down matrices and multiply them, then you see it's not too much more difficult to multiply complex matrices compared to real matrices. It's a little more complicated, but not a whole lot really. But then in practice, you see, as you scale the problem up, you cannot really afford to write down matrices and multiply them. Why? Because the matrices are 2 to the power n by 2 to the power n. And as we know, as n goes up, this 2 to the power n just goes up exponentially. And very soon it's out of control. And so writing down matrices and multiplying them is not practical when you scale up. So what do you do? Well, for practical problems, you use sampling techniques usually. And how do you sample them? Well, I guess in weeks 2 and 3, we discussed these sampling techniques. How you can operate in this n space and generate samples in the 2 to the n space. And 2 sampling methods we talked about. We talked about Gibbs sampling, and we also mentioned the Metropolis algorithm. The idea is that you generate configurations one after the other, configurations in this 2 to the n space, and given a configuration, the way you choose the next one is based on the energy of these two possibilities. So you choose the next one according to the probability ratio of where you are and the new one that you're considering. And this ratio is obtained from the energies. And as long as you can write down the energy for a configuration easily, without doing 2 to the power n calculations, you can keep generating samples efficiently. And as you generate samples, you create a histogram, and that's how you finally get a good approximation to the final probability distribution. Now, in this context, you could use the same method. You could use the same sampling technique. You see, the way you do it is, you look at this graph, the way you're going from 0 to 0 or 1, etc. And then consider a path, a path that goes 0, 1, 1, 0, etc. And view that path as the state of a giant Boltzmann machine. I say giant because usually we think of Boltzmann machine with n bits, but now you have to factor the t into it, namely how many times steps there are. So it's a Boltzmann machine with nt bits. And there are 2 to the power nt configurations. And if I wrote down the amplitudes of all of them and added them up, I'd get the exact answer. But what we want to do is kind of sample those configurations and come up with an approximate answer. Now, what we could do here is we choose a particular path and then write down the amplitude for that path. And then the next one we consider, again, write down the amplitude. And just like your old sampling techniques, we use the magnitude of this ratio of amplitudes to decide to choose the next configuration. So methods would work just like before, but the amplitudes are now complex, and we'd use the magnitudes to decide the sampling. But then, because these are complex, the thing is, we have to, when adding up the different paths, adding these up, you don't add them up like, okay, I got one sample here, one sample, and add them up 1 plus 1 plus 1. You add up complex numbers. It's because every path has an associated complex number with it. So that's what you add up. That's the phase of this AI, of these different paths. And that's the essence of this method of quantum Monte Carlo, where people use sampling techniques to solve quantum problems. So this problem we were talking about, like there is a correct output, the one that you started in 0 and you end up at 0, and then there's a wrong output, which is the 1. Now, when you do it with sampling using this method, of course, it is not as if there are no samples for this wrong output. There are plenty of samples. It's just that they have different amplitudes, some positive and some negative. See, in general, the amplitudes could be complex, but for the Hadamard gate, it's just +1 or -1. And the point is that you have lots of samples, but they cancel out because some are positive and some are negative. Now, if instead of the Hadamard gate, we had been using, say, the Pauli X gate, the one that up becomes down and down becomes up, then you see there are no negative signs here. And in that case, again, you'd still have just as many paths. But the wrong output now, all the paths would have amplitude of 0. Any path that reaches that wrong output would have an amplitude of 0. So what that means is, when I'm collecting samples, I'd never get any samples here. So if I, say, took 1,000,000 samples, they would all end up there, which is very different from what we are having with the Hadamard gate, where although at the end of the day the answer is 0, but still a good many samples, good fraction of my 1,000,000 samples will actually end up there. And I'll have to add them all up to cancel them out and get a 0. And that makes it very inefficient, see? And this is where, of course, if you had qubits and a quantum computer, then it shines, because the qubits instinctively know that they should avoid this wrong outcome. So when you have qubits and you collect samples, none of them go to the wrong answer. Now, in this course, we have talked about classical optimization. If you remember, there's a max cut problem we considered in week 2, and there we had an example with six of these spins, classical spins, with 64 possible states, 2 to the power 6, and there were 2 peaks which showed us the answer. And more recently, this week, we did the Shor's algorithm, and this is an example with just 4 of these quantum spins. And again, we had 2 peaks in the output. But there's a big difference between the two. That is, in our classical example, you see all these nulls, the place where the answer is 0. if you sample it, no samples will ever reach there. But in the Shor's algorithm case, there are samples that reach there but then actually cancel out. So this max cut problem, the classical optimization problem, you may remember, we revisited it in week 4 and used it as an example for adiabatic quantum computing as well, where you have to calculate the density matrix. Now, although we have not discussed it, actually this density matrix can also be evaluated by sampling Feynman paths. And in that case, people make this distinction between stochastic Hamiltonians and non-stochastic Hamiltonians. Stochastic ones are the ones where paths don't cancel. They all have the same sign. And so sampling is very effective. Whereas non-stochastic is where paths are actually canceling out. Now, this week though, we have been focusing largely on gated quantum computing, which is based on wave functions, and there's this transformation matrix here. And one example we gave was the Shor's algorithm, where the one important operation there was the quantum Fourier transform, where you had a matrix looking like this, where P is a phase factor. And we argued that when operating on a wave function looking like this, it gives you 2 peaks. But the point is these 2 peaks arise because of cancellations, in the sense that if this phase factor, instead of being a complex number, had just been 1, just positive number 1, then we'd have got samples all over the place. When you multiply this matrix into this wave function, all the terms that would come in, they would all be, they're everywhere, they would be all spread out, etc. Now, why is it that by putting a complex number we got only 2 peaks? Well, for all these in all these states, what happens is when you add up various things, they cancel out. But for the correct ones, they don't cancel. And this is where, of course, if you are trying to emulate this by sampling, again, on a probabilistic computer, you have to take many, many samples to get the proper cancellation. Whereas a quantum computer would the qubits would just instinctively never reach those null points. Of course, that's true of the ideal computer, the one that's noiseless. In the real world, we have to deal with noise because the quantum computer is in touch with its surroundings, which have noise which destroy the phase. And when the phase is destroyed, of course, the problem is that these samples cannot cancel very effectively and give you nulls. And so there is this worldwide effort at this time on evaluating how well noisy quantum computers can actually perform or enhance the performance compared to classical probabilistic systems. Well, that brings us to the end of this third part of the course, the last 2 weeks, 4 and 5. And if you're taking the exam, you might be interested in a quick summary that we have put together. And in any case, I hope you'll join me for the short epilogue that follows. Thank you for your attention.